Okay, thanks everyone for coming to the first QFT in Physical Mathematics seminar. Just for those who don't know, this is a continuation of the Quantum Matter seminar from previous years. And we're really happy to have our first speaker, Zhengcheng Gu from the Chinese University of Hong Kong. He will talk to us about the classification and construction for crystalline topological superconductors and topological insulators in interacting fermion systems.
Thanks. Yeah, I think this topic is probably closely related to what Dan did maybe 5 years ago, but I think we just have slightly different point of view from the physical side, and we also want to really visualize what's the precise explicit construction for those crystalline state. And yeah, as a physicist, we hope we have some material we can really measure, yeah, what kind of like phenomena, for example, on the surface, on the corner, yeah. So it's also related to this so-called higher order, higher order edge states. Yeah, so I will explain later. So yeah, we have a few works. I think if you're interested, you can just briefly read up on these works. So basically, in the past 5 years, I spent some time on this topic, and we also developed some algorithm. Like this is an algorithm paper. We can actually try to rigorously compute this Hertzsprung spectrum sequence by using this software gap. Yeah, if you're interested, you can find this this open source code on the gap. There's GitHub probably. yeah, there's like a website. Okay. Okay. Yeah, of course, our final goal. Hopefully we can also classify this whole 230 like space group. But this computation is really hard at some point, so we're still continuing doing this computation. And yeah, just the sum of those like space group is really hard. And yeah, even this gap software does not work well, so we try to have some other way to compute it. Hopefully, we can finish by the end of this year. Okay. So I think yeah, maybe I assume yeah, many of you probably heard about this name about the like symmetry protected topological phase, right? Yeah, maybe someone not, but I think it's a topic Dan will be very familiar. And yeah, it's some like a physical progress in the past 20 years, almost past 20 years. Yeah, people talk about the discovery of topological insulator, and yeah, it's kind of a special immutable phase in the mathematical terminology. We call it immutable phase, but protected by certain symmetry, like time reversal symmetry, charge conservation symmetry, so on and so forth. And the recent years, I think later, I think after this discovery, Liang Fu, professor from MIT, he proposed that yeah, even with this crystalline symmetry, maybe there could also be some non-trivial insulating state. So yeah, their argument again starting from this free Fermion system to look at the surface. I think yeah, a lot of like interesting phenomena arises on the surface. Okay, so I think yeah, later people also have more rigorous like mathematical understanding for this classification from the K theory, also yeah, from this so-called twisted K theory by Dan Frey, probably yeah, it's talked like almost more than 10 years ago. Yeah, first met Dan in Sanya. Yeah. So that's I first heard about this and try to learn from that time. Okay, so but from the material point of view, we also understanding this kind of crystalline SPT phase widely existing in interacting system, not necessary to be limited in free Fermion system because yeah, just give you a very simple example. This is so-called spin-1 Howland chain, and this spin-1 Howland chain for a long time people understand it's some kind of SPT phase, right? But usually we just refer it as SPT protected by a certain internal symmetry like time reversal or spin rotation. So we talk about like symmetry fractionalization, like spin-1 half-degree freedom on the edge. But actually in our first work, we kind of try to confirm it's really protected by symmetry. We just try to study such kind of Hamiltonian. And this Hamiltonian is actually break both rotation and time reversal. Yeah, so naively it looks like, oh, it should be unstable, but actually not. It's still, you can see some very stable phase. And the reason is that there's still certain lattice symmetry remain in this model, namely this reflection symmetry. Yeah. So once we have this reflection symmetry, it's still some distinguished phase. However, yeah, some kind of symmetry fractionalization phenomena like this spin 1/2 degree freedom. Yeah, we can no longer talk about those things. It's just a kind of we have two different phases. But
that model still has a Z2 spin reflection symmetry, right? That's not.
Oh yeah. But the Z2 spin reflection itself is not enough to define certain SPT phase because yeah, this projected rep for the Z2 symmetry is trivial. Yeah. We at least need a 2 Z2. Yeah, if you have 2 Z2, we can still define some SPT phase like a cluster state.
Okay, so then you're saying in this case, there's one of the Z2s is translations or something?
Here actually, yeah, in this model, we're talking about still the essential symmetry, important symmetry is the mirror reflection. Yeah, so that's our actually we emphasize this in our first paper. So if you completely remove the mirror reflection in this Hamiltonian by adding certain perturbation, yeah, then Howden phase trivial phase, yeah, they're just connected. Okay. No phase transition. Okay. But actually at that time we also observed that it's slightly different from the usual SPT phase protected by internal symmetry, because usually we expect there should be some kind of symmetry fractionalization. But actually in this case, if you carefully do this numerical calculation on the edge, there's also no symmetry fractionalization. Yeah, so more rigorously, I think people doing math sometimes they call this as a torser, not really kind of we can define some canonical kind of trivial phase. Yeah, but that's some subtlety here. So let me before talk about this subtle things, let me just tell you some other simple picture to understand why this mirror reflection can protect this phase. So that's also also in a following paper by Frank Pullman. They just point out that they actually very simple way to understand why on the mirror reflection is non-trivial, because you can just think about this 7 spin spin chain. Yeah, actually you can use any type of order number. Yeah, then you just think about we have a mirror-like line. You're doing this kind of mirror reflection because this singlet, spin 1/2 singlet is like a parity order, right? You exchange this to spin. Yeah, it's up down minus down up. You exchange them, you have minus sign. So actually this type of wave function, if you think about the order number of sides, you're doing the reflection, there's some eigenvalue -1. So now we call it mirror eigenvalue -1. But for the completely trivial phase, suppose you think about the product state, yeah, then you don't have this kind of singlet bound. Then just mirror eigenvalue +1. So this is a physical way to say, oh, this is kind of non-trivial because it have a mirror eigenvalue -1.
Also, the eigenvalue depends on the system size. That's also important.
Odd, yeah, anything odd, yeah, even that not work. You should choose odd. Yeah. Then I think later some people use this more rigorous method, yeah, and some picture to try to say that the classification of this kind of Crystalline SPT phase and internal symmetry SPT phase, there are certain kind of correspondence, yeah, this by Els and Ryan. I think that's a kind of some argument, and also later more rigorous proof by Yang Qi and his collaborator, and based on this kind of spectrum sequence method. Basically, in this bosonic case, you can just use the coordinate formula and you can show this correspondence very precise. And in the meanwhile, they also propose this so-called block state decoration scheme. I will explain in minutes. So yeah, that's a very simple way to understand this so-called crystalline SPT phase. Yeah, so that's even much more simple than those internal symmetry SPT phase. We can really visualize it as maybe so be familiar, something like valence bound solid state. Yeah, we only have one configuration. We don't think about the superposition of the wave function. So for this internal symmetry SPT phase, it's like we need a fluctuation of domain. So it's something like RBB state. We need the resonant those configurations. So here we just revisit our Howden model. Yeah. So again, now we think about a case. Yeah, it's just protected by time reversal symmetry. We already know that's well known. There's a Z2 classification, right? We can use this spin 1/2 degree freedom to identify the non-trivial phase. But now we think about how to understand this mirror reflection symmetry classification. Yeah, so there's a very simple argument. Suppose we only have mirror reflection symmetry with respect to this point, right? So then on the right hand side, there's no symmetry at all. Left side also no symmetry at all. So I can imagine I can do some local unity transformation. I make this thing pretty trivial, just a product state. Then I make a mirror reflection to this side, it's also product state. So the only thing you can, non-trivial thing you can think about is in the middle point. Yeah. So in the middle point, this mirror reflection just acting as like a Z2 onside symmetry. Then from the mathematical point of view, we know that this kind of Z2 symmetry, we have eigenvalue +1 or eigenvalue -1. Yeah, so yeah, it's kind of this -1 just corresponding to the previous argument for the AKOT state. Yeah. So we call that kind of non-trivial phase. Okay. So now we also see in this example, yeah, this we verify this correspondence in a very easy way. If we think about time reversal, it's have a Z2 classification, but mirror reflection also Z2. But in their correspondences, they state that yeah, for any kind of rotation symmetry, just map to internal Zn symmetry. Rotation Cn just map to internal Zn. But for this like mirror reflection, we should treat it as an anti-unitary. So basically become time reversal. Okay, so that's a very simple statement for the bosonic system. Any question?
By mapping the symmetry to internal symmetry, you mean map between two different systems, or?
Yeah, I mean map between two different systems. Yeah. Okay. So now I try to, yeah, that's essential part of this talk today is about the fermion system. Yeah, but I believe people doing math are very familiar with this kind of so-called definition of fermionic symmetry. So this is like a short exact sequence. It's just like a fancy way to say that this Z2F is a normal subgroup and the GF is a total symmetry. So you can also use this quotient group notation like a GB, the bosonic symmetry just equals to this GF, the total symmetry quotient by Z2F. So this may be the language for physicists much easier to understand. So yeah, sometimes we talk about our T squared to -1 for fermion system or +1 for fermion system, right? So -1 actually means it's a non-trivial extension. We actually mean -1 just minus to the fermion number, -f. Yeah, so for fermionic parity order state is minus, and the fermion parity even state is +1. And also, yeah, here just can show you why this is related to this second group of homology class, because yeah, this extension completely determined by this classification of this this cohomology class with Z2 coefficient. Yeah, so here you can, when you see this multiplication of these two group elements, how they extend to GF, you can see there should be some omega twist factor. And if you require this associativity relation for the group multiplication, you will see it should satisfy these co-cycle conditions. Okay, so that's a very simple reason why this quantity involved when we define fermion symmetry. And that's a very important part, because when we talk about the fermion, we should be specify what's the omega 2 extension. So that's typically we talk about like for spin 1/2 system, it's a non-trivial extension. Spinless or spin 0 system, it's a trivial extension. Okay. So now let me just again give you some very simple example for 1+1D fermion system. Yeah, we want to do this kind of exercise again. So we think about this like a spinless fermion system first. Then we again think about this mirror reflection m squared to +1. So that's the simplest example. And then now you can see the group structure basically just a Z2 tensor product Z2F, which means there's no omega 2 extension, right? Now we can just apply the same kind of decoration scheme. Yeah, so you imagine what we did for the bosonic system. We try to understand this crystalline SPT for 1+1D system. We just decorate like mirror eigenvalue +/-1 in the middle. It's pretty trivial. But for fermion system, we have something more we can do. Like we can put a fermion parity odd, or even we put a fermion or don't put a fermion. We have this additional kind of degree of freedom. But in the meanwhile, of course, we still have this +/-1. But here I just want to argue this like minus eigenvalue. Now in this case become trivial, because you can think about it, you can create a pair of fermion on both sides in a symmetrical way, don't break the symmetry. So this can be realized perfectly by this local unitary symmetry respect to the mirror reflection symmetry. Yeah, then you just exchange them, you generate this -1. So in this case, yeah, we just say, oh, this classification just become trivial. Okay. But of course, in fermion, in principle, we can have something more non-trivial. You can say, oh, on this like half infinite chain, we can also put something we call a Majorana chain, right? So that's we know the only immutable fermionic state, right? Yeah, in principle we can do this, but now I just show you actually this there's an obstruction to do this. The reason is that also very simple. If you just write down this Magana Hamiltonian, it's a summation of this I gamma 1 gamma 2, right? You do this mirror reflection. So gamma 1 become gamma 2 become gamma 1, you have a minus sign. So that's also not a symmetric kind of master. It's not allowed. Yeah, so now in conclusion, we only have this first declaration worked out. So we only have a Z2 classification, but if you match this classification for D3 class, the D3 class just means we have time reversalities for the -1. So we know there's also a Z2 symmetry, Z2 classification. So again, kind of due to some mystery reason I will explain later, it also matched pretty well. But now we have some twist. People also realize this twist. I think in early days. Here when we talk about crystalline symmetry, it's mirror square group +1. But when we map to this internal symmetry, become time reversal square group -. So this kind of interchange, this kind of twist is very important. But also you can do the exercise like with this m squared to -1, then you get some Z8 classification, so it become the BD1 classification for the time reversal symmetry. BD1 we know that T squared to +1, so it have a Z8 classification. The cross by Pidai, so everything matched pretty well. So it looks like there should also be some correspondence, but we don't know so far. Okay. Now we doing this exercise a little bit more complicated. We try to go to 2 dimension. Okay. So 2 dimension, the point group. We first before we work out this full like space group, we just focus on the point group first. But point group in 2D is very simple, just like a CN rotation or and a DN symmetry, right? But DN symmetry just means you have some additional kind of mirror reflection symmetry, which is not a commute with a CN symmetry. But for this CN kind of phase, there's also many studies because the nice way is that they can be realized in free Fermion system, and people also talk about some reduction from free Fermion system. But of course, you can again use this block state construction. It's very similar to the 1D case. So I think I'm not going into detail, but if you're interested, you can take a look at this papers. We also have this full classification results. Basically the scheme is very similar to the 1D case. 1D everything can also be realized in free Fermion. So we can do this declaration, but more is like reduction from free Fermion system, because in interacting system we allow to add more terms to reduce the classification. Okay, but for the DN case, it's a little bit non-trivial, and the most non-trivial example is the D4 case, because here the conclusion is that for D2 it's just a Z2 classification, D6 also just a Z2, but for D4 it has a Z2 times Z2 classification. So there's an additional Z2. And this additional Z2 turns out to be quite non-trivial, because that's the first example of crystalline SPT phase, which cannot be realized in free Fermion system, non-bosonic system. So it's also an intrinsic fermionic interacting SPT. Without interaction, there's no way to realize it. So now we want to see how to work out this D4 example, for the classification. So I will mention later, you can, again, in this case, you can also map into internal symmetry. And it also perfectly agree with the classification. But here now, let me just again show you this real space construction. Because real space is more physical and related to this material, we can actually try to observe certain kind of non-trivial, for example, corner Magana mode in the material. The header, so just like a C4 semi-product, like a mirror reflection. I will explain what's the group operation. Basically, here just like in this cartoon, we divided this into 8 pieces. That means we call it Sept computation sometimes. So that just means this D4 group has 8 group elements. So it has this C4 rotation map U to R, U to R square, U R third U, right? And if we do the mirror reflection, U to M U. So now you can see why this 8 pieces corresponding to 8 group elements. But it's a semi-product. This 2 group operation not commute. Here it's everything I'm talking about today is crystalline. So I will show you this correspondence later. In the end, I will show you this correspondence for how things go in when we map to this internal symmetry.
So here is a C4 rotation semi-derivative.
Right. So here everything I'm talking about just the crystalline symmetry, crystalline operation. Yeah. So in this block state construction still works. Yeah, you can think about this blue shaded region. There's no symmetry at all because you add symmetry just map to some other blue region, right? So now you can think about that. You can do this very similar trick to the 1D case. Yeah, I just trivialize this region, become a product state. And then I map all the 8 pieces, it's just a product. So something non-trivial just in the middle. Yeah, in the middle, this we call high symmetric line. So this high symmetric line, there's still residual symmetry. Yeah, this like, for example, this mirror reflection with respect to this line becomes a Z2 internal symmetry. So it has enhanced the symmetry. So high symmetric line with enhanced symmetry, we can put something non-trivial. Yeah, we'll explain it later. And then you can expect you can construct some non-trivial phase. But yeah, in the blue region, everything just product state, pretty trivial. But of course, we can also decorate something even non-trivial like in the middle. But of course, this decoration is just a 0 dimension. It's also easy. Just a 1D example. Yeah. So yeah, so here's the formula. Sometimes we call it symmetric trivialization. So after trivialization, all these shaded region just product state, and non-trivial things just localized onto this high symmetric line or high symmetric point. Yeah. So that's the principle of this block state construction. Now we try to analyze how many 1D block state we can have. Yeah. So again, very similar to the 1D case, we can have this Lagrangian, which is unallowed in multiple phase, right? So we can like try to decorate onto this, for example, 1, 2, 3, 4. Yeah, but here we see we can have 2 different classes because 1, 2, 3, 4 on the mirror reflection just map by themselves will not fix with this ABCD. So in principle, we can just decorate half 1, 2, 3, 4 to preserve the symmetry. But it's easily to check. Yeah, actually, it's not allowed. And also, if we try to decorate 8 with 8 major mode in the middle, yeah, unfortunately, it's still not allowed by symmetry. And in order to see this, it's actually very simple to see this. Suppose we only like decorate on 1, 2, 3, 4. Then you can see on the rotation, you just want to make a cyclic permutation of this 1, 2, 3, 4, right? Yeah, then we generate a minus sign. So that means the rotation is not compatible with this line with this such kind of decoration pattern. But even you decorate 8, still not compatible because yeah, in any case, if we do the mirror reflection, you just reflect all the number of pairs. You always generate a minus sign. Yeah, so that's such kind of root state still not allowed. But now we have something more than 1D because, as I mentioned, there's like residual Z2 symmetry. Originally, you can think about it as a mirror reflection symmetry, but localized on the 1D line becomes an internal symmetry. So now we can actually talk about like Z2 SPT state, yeah, with this additional Z2 symmetry, together with a Z2 fermion parity conservation. Okay, so again, it's a Z2 times Z2F 1D SPT. But these things we know pretty well. The complete classification we also understand. Yeah, there's a non-trivial kind of fermionic SPT state we can decorate in this case. Okay, and this is the fermionic root phase again can be realized by free fermion system. Basically, it's just like a double Lagrangian chain. Yeah, so that's a very simple way to visualize this Z2 times Z2F fermionic SPT phase. And this double Lagrangian chain has a property that under this kind of Z2 action, for example, if you think about the vertical Z2 plane, then this is just mapped to that 2 and 4 just exchange. But on this mirror line, this 1 and 3, they just act as an internal symmetry. Yeah, so in order to make this symmetry to be non-trivial, then the action on gamma 1 does not generate a sign. But in the meanwhile, one of them must generate a sign. So if you choose gamma 1 prime map to gamma 1 prime, then this gamma 1 should map to minus gamma 1. If both of them do not generate a sign, yeah, then it's just a trivial Fermion SPT state. Okay, so that's our rule. So now you can see this is a symmetry action. Yeah, on the rotation, just doing this cyclic rotation. But on the mirror reflection, there must be a minus sign. It's very important. If you put I in the 1, that means this gamma 5 equal to gamma 1. So gamma 1 maps to minus gamma 1. That's very important. And the gamma 1 prime maps to gamma 1 prime again. Now we end up to like 8 major modes. Yeah. So we can still ask whether we can design some in typing term to gather them out in the bar. If we can gather them out, such kind of decoration is allowed. Otherwise, it's not allowed, right? Yeah, just like we decorate a single Madonna chain is not allowed because there's no symmetric term. We can gather them out. But this kind of gap component is very easy to construct. Yeah, so we again use a physical way to do it, and it's try to simplify the classification. But you can actually find some very nice kind of rigorous commuting projectile Hamiltonian, but not so simple. Yeah, so in the physical way, we can think about this and realize as two steps. So first step, just like the total parity of this 4 Majorana modes, yeah, group 1 and 3, 2 and 4. Yeah, so this is just a Fermionic parity operator. Yeah, if we in the limit U very big, both of them take the eigenvalue -1. So it's kind of a project the subspace. But this one term is still not enough because here this 8 Majorana mode form this like 4-dimensional Hilbert space. Yeah, if we only add this one term, we still have a twofold degeneracy. So we still need to add more terms. So the other term also easily to guess. Yeah, within this subspace, you can easily verify gamma 1, gamma 1, gamma 2, gamma 1 prime, gamma 2 prime. And these two terms, they also preserve the symmetry under this subspace in the large unit. Okay, so now we can make the conclusion. We can just add some interacting term, but it's very important. They are not Majorana mass. It's intrinsic interacting term. Yeah, so the story is very similar to the BD1 class. If you just think about the performance mass, you have a Z classification, but if you allow to add a 4 Fermion term, then you make a Z8. Yeah. So here it's very similar. If you allow to play interactions, you can get them out. So this decoration is allowed, but in the performance classification, it's not allowed. So that's why we can get more cases for the crystalline Fermion SPT. However, similar to the 1D case, yeah, in 1D, I just argue like the mirror eigenvalue -1 sometimes become trivial, right? Yeah, so we should be careful about this. Yeah, so we still want to ask in a physical way whether the state we construct is trivial or is really non-trivial. But as a physicist, we at the beginning we just don't know how to prove it, right? So we just want to make some argument. Yeah, but this is a physical way to argue. So you imagine you can make some disk. Yeah, so this disk prepared in the lab, and then you just like decorate the Majorana chain, double Majorana chains on this 1, 2, 3, 4, this high symmetric lines. Yeah, then in the end you end up with this 8 dangling Majorana modes. Right? Yeah, then you can imagine on the disk, on the boundary of the disk, there are 8 Majorana modes. Then in the lab, people try to, for example, just attach some open Majorana chain in the boundary. Yeah, after this attachment, we just ask whether we can get out these 8 Majorana modes in a symmetric way or not. If you can actually get it out, then it's identical to the trivial phase because in the lab, we don't know on the boundary there's existing open Majorana chain or not because you always allow to attach some one-dimensional invertible phase. So looks like, this kind of, we can get them out in a symmetric way because you can focus on this group of Majorana mode. Yeah, if we do the mirror reflection, we just map, yeah, because acting on gamma 1 must generate minus sign. That's very important. Gamma 1 prime go back to gamma 1 prime. The gamma alpha delta just exchange because that's the things that you decorate on the surface. Then, you see the total Fermionic parity just commute with the mirror reflection. Looks like we allow to put some 4 Fermion term. Yeah, just a multiplication of this 4 to gather them out. But actually, there's something subtle because we not only consider reflection in the vertical and horizontal direction, right? We actually, for the D4 group, we also have reflection on the diagonal direction. Yeah, but on the diagonal direction, we are going to like cut this Majorana chain. So that operation we already know from the 1D lessons. It's not allowed. Yeah, if we think about the mirror reflection m squared equal to +1, it's only allowed for the -1. Okay, so now we end up with the idea that maybe we can just if this decoration of this 4 Majorana chain is not allowed, how about decorate 8? Yeah, decorate 8. If you still remember our kind of high symmetric high symmetric line, we have 8. Yeah, this 1, 2, 3, 4 is group 1, ABCD group 2. Yeah, so we just ask question. will happen if we decorate this 1D fermion SPT state on all the 8 high symmetric lines. Yeah, so both 1, 2, 3, 4, and A, B, C. So in this case, our argument for this obstruction for this diagonal structure vanish. So indeed, we can gather them out. But in this case, what's the physical meaning? It just means our decoration for either 1, 2, 3, 4 or A, B, C, D, they are equivalent. Yeah, we only have one Z2 class. We're not going to have 2 Z2 class because either 1, 2, 3 or A, B, C, D is the same non-trivial state. If we decorate all of them, it's trivial, right? Okay. So now we find this non-trivial Z2 state. So you can do the similar exercise for D2 or D6. Yeah, D2 or D6, you only have, for example, D2 only reflecting along one direction. In that case, it's easily to check such kind of decoration is not allowed. So D6 is also not allowed. So that's why for the D4 case, we have this additional Z2. Yeah, so this is a kind of a physical way to visualize the results. In order to get the complete classification, yeah, we can further think about this 0-dimension decoration. Yeah, so that's pretty simple. It's the same exercise as the 1D case. It basically just compute this kind of one-dimensional representation for this total GF. Yeah, it's a 1D representation for the total GF. But in the computation, we just split in 2 pieces because yeah, in this case, very simple. GF is just a tensor product of this D4 and Z2F. Yeah, so this is actually F0 is a contribution for the Z2F part. So kind of we can again put the Fermi parity even odd on the on this high symmetric point. Okay, but for the D4 group, it's 1D representation. It's Z2 squared. So naively, you think about, oh, we have Z2 cube classification here, right? But again, we should worry about whether such kind of mirror eigenvalue can be trivialized or not in a fermion system. This case, if we talk about spinless system, yeah, indeed we can again similarize 1D case. We can trivialize all this reflection and this mirror and rotation eigenvalue. Yeah, so the way you think about this, it's very similar to the 1D case. Now you can think about we can decorate the 4 fermion. 1, 2, 3, 4. Create a 4 fermion in a symmetric way. Yeah, and this 4 fermion you can do the cyclic rotation. Generally, there's -1. Yeah, so that makes this rotation eigenvalue trivial. Yeah, similar for the mirror reflection, you just reflect a pair similar as 1D, also make it trivial. So now the conclusion is that we again only have this 1 Z2. So now we finally understand why we have this Z2 squared classification for D4 and only 1 Z2 for D2 and D6. Yeah, for D2 and D6, we only have this Fermi parity. It's the same as a 1D case. There's nothing else. Any question? Yeah, so I think yeah, that's the 2 simplest example I want to explain before going to more generic case. But I just briefly mentioned this difference in the spin 1/2 system. Oh yeah, we have the result. Yeah, D2 doesn't have Z2 classification. D6 also Z2. Yeah, but basically there's like for D2n, when n is even, you have Z2 squared. N is odd, you just have a single Z2. So that's the result. But for spin 1/2 system, yeah, if we go back to our previous table, yeah, we always just get a Z2 squared classification. I also want to emphasize this Z2 squared. They just purely bosonic SPT states. There's no non-trivial fermionic SPT phase. The reason also very simple. Yeah, you can again think about the block state decoration scheme. For spin 1/2 case, the total symmetry in consideration on the 1D high symmetric line is Z4F. Yeah. For Z4F symmetry, I think also from previous calculation, we know there's no non-trivial 1D fermion SPT phase. Yeah, even this chaotic chain, this immutable phase is not allowed under such kind of symmetry. So there's nothing you can decorate on the 1D block. The only thing you can play with is just this 0D block. But for the 0D block, again, we need to think about the 1D representation of this, yeah, the 1D representation of the total symmetry group GF. Yeah. But in this case, it's a little bit tricky because this Z2F is a non-trivial extension over this D4. So again, we can compute the 2 pieces of data. But yeah, this Z2F part, if you decompose this into 2 pieces, yeah, there's an obstruction function. Yeah, so in this case, you can see it's obstructed. So it will kill one Z2 root phase, which means physically just means you decorate all the number of fermions not allowed in this case if it's non-trivial extension. Yeah, it's also easy to understand it because this Z2 non-trivial extend over the D4, then you only have 2 non-trivial 1D representation, not 3. Only have Z2 square. Yeah, two non-trivial root phase, not 3 non-trivial root phase. But this Z2 square, again, very easy to be understood. It just, again, this rotation and mirror eigenvalue. But in this case, you can see also something different happens. Because in this case, it's a spin 1/2 fermion, right? That means after 4 times of rotation, after the quartic should be -1. And also mirror reflection M squared should also be -1. So the way to argue why in this case you cannot kill this mirror reflection and rotation eigenvalue -1, just because under this rotation for spin 1/2 system we should put this -1 to make sure R positive minus or M squared minus. Yeah. So in this case, you're doing the similar operation, then this let's say just go back to the same one. So cannot generalize this generate this -1 eigenvalue. So now you can see the final result just D2 square. Yeah, for both for all the cases, D2, D4, D6. Yeah. Okay, so now we have a complete understanding for this point group for 2D system. Yeah, so we can use this kind of result to construct a generic space group in 2+1D. So I just show you the result and yeah, briefly describe the scheme. So the whole talk is 1 hour or 1/2 hour?
You can go as long as.
Yeah, maybe I try to finish in 1 and 15 minutes. Okay. Yeah. Okay. Not make it too long. But now I just explain the generic scheme. Yeah, it's very similar to our exercise for the point group, but we want to make this more systematic. So we just list 3 basic steps. One is just step 1. Yeah, just a so-called cell accommodation. It's very similar. Yeah, we want to decompose this space into cells. Yeah, satisfy all this group symmetry operation. And then we make this 1D block and 0D block declaration, very similar to our scheme for the point groups case. But yeah, so for this discussion about the trivial or non-trivial point, yeah, we want to also make it more systematical. So we call this bubble equivalence principle. Yeah, so I will explain later what's the meaning of the bubble. So that's a more systematic way to judge whether the constructed block state is trivial or non-trivial. Because previously we just use some argument. It's not some rigorous scheme. Then once we know this is so-called trivial block state, yeah. So if we can consider the block by using this bubble kind of equivalence, they are all trivial, right? So the final classification group result is just a quotient. Yeah, this observation-free block state quotient by the trivial block state. So that's a precise definition. So again, we just look at one example. So in this case, we think about the P4M space group symmetry. Yeah, so for the P4M case, the cell decomposition is a little bit complicated, but anyway, you can find all the cell decomposition on Wikipedia. Okay. So the nice thing is that this whole thing is just like nicely act under this translation. So each cell you can think about it repeated by translation. Okay. But now in this within this cell, yeah, it's slightly complicated than the example we studied before by purely D4 point group symmetry. Because there are different types of rotational points. We have this mu1, mu2, mu3. Yeah, their symmetry is different, slightly different. You can see this P4M case. If we think about this 0D block, yeah, this 1 and 3, it's actually it's a D4 kind of rotational point because it can really perform this full D4 symmetry. But for this mu2, it's just a D2. Yeah, there's no way to perform this full D4 symmetry. Of course, the 1D block, they are all the same. Yeah, you only have this Z2 reflection symmetry. It's now become unsized. And the 2D block, there's no symmetry at all. Now we can repeat this declaration scheme. Yeah. So because here we just think about SPT, not all the invertible states. So we don't worry about this 2D block. 2D block, what you can do is just P plus IP. Yeah, but also there are some subtle detail whether this P plus IP comparable with the mirror reflection or not. So I'm not going to that part. Yeah, for SPT, we never worry about that part. Okay. So yeah, as we explained before, for this 1D block, the only non-trivial thing is this 1D Fermionic SPT phase. Yeah, we can decorate. But the conclusion is that now this classification becomes Z2 square instead of single Z2. The reason also very simple. For example, if we just look at this mu3, the reason we only have mu1 and mu3, two types of D4 0D block. So surrounding mu3, we can do in this double modulation decoration, right? So that's one allowed block state decoration. But we can also do it in the other way. Yeah, but the other way is a little bit tricky. We should do the double modulation decoration on both pole 1 and pole 2. Yeah, on pole 1 you can see it's just like surrounding this D4 0D block. Yeah, so it's perfectly allowed. But we know this 1D SPT decoration surrounding this D2 block, mu2 is not allowed. However, if we decorate this both vertical and horizontal, that's something just you remember our argument. If we decorate 8 for this D4 case, it's trivial. But here it's if we decorate 4 for D2 case, again it's trivial. So it's allowed, but just here there's nothing non-trivial. So that just means we decorate this pole 1 and pole 2 together. It's a non-trivial decoration. So now we get this Z2 square classification. Okay. So that's all the allowed independent 1D block decoration. Okay, so next we already know that for this 0D block, each 0D block, mu1, mu2, mu3, yeah, we have this Z2Q classification. So now looks like without talking about any trivialization, we have Z2 together with the Z2 square, we have Z211, right? But of course, we know there are not so many classifications for the P4M space group. Yeah, there are also something should be trivialized. So we want to consider this slightly careful. So yeah, we first talk about this 0D block. 0D block is very similar to this case with purely point group symmetry. Yeah, so surrounding this, for example, D4 mu3 point, we can also create a 4 and make this like mirror reflection eigenvalue, rotation eigenvalue trivial. Yeah, and also, but here you can see we should prepare this Fermion by pairs. Yeah, so slightly different from the infinite chain. But of course, we have like 3 independent bond or 1D block. We can create this pairs. Yeah, so basically you can discuss all the trivialization possibility. There's also the independent one, just Z2Q. But for this trivialization for the 1D block, yeah, we also need something more systematic to argue. So in this way, we call it the 2D bubble. You can imagine, before for the D4 case, we just argue, for this all 8 chains, if we decorate this double modern chain or 1D Fermionic SPT is trivial. But now we use a slightly different way to visualize these results. Yeah, we think about each like a 2D block, we call it sigma. Yeah, sigma basically there's nothing there. But we can think about starting from nothing, you make a very small loop of 1D modern chain. Of course, you can make the pure anti-periodic boundary condition, make sure it's a Fermion parity even. Yeah, so then you can make 8 pieces of small modern chain. Right? Yeah. Now you can just the microscopic argument is just cut them at the corner and reconnect it. Yeah, so eventually you can have something like this. So in this case, we end up with an argument. If we decorate all these pole 1, pole 3, pole 2, pole 3, make all of them decorating by the 1D Fermion SPT. Again, it's a trivial state. Yeah. So this kind of double equivalence argument is exactly the same as our argue anomaly cancellation boundary. Yeah. So, but this is a more systematic way. So now we can see this quotient group. This for 1D block again it's Z2. So in total we have Z2Q trivialization. Yeah. So we trivialize one 1D Z2 block. We get a single Z2 left. But this is a fermionic root phase, similar as the D4 point group. Now we also have this another kind of Z2 trivialization out from this Z2-9. So we have Z2-6. But here I just use different color. Just means half of the Z2 cube is kind of we put the fermion parity even or odd on the 0D block. So the red part it's a fermionic root state. And the blue part just a bosonic root state. It just means the mirror eigenvalues kind of plus or minus 1. It's less interesting. So this red part is always interesting because it's some like a fermionic state, and we can expect some non-trivial things may happen on the boundary. So in conclusion, now we can see this classification just Z27. Yeah, we have 4 fermionic root state and 3 bosonic state. But if we apply a similar construction for the spin 1/2 system, then if you still remember our conclusion for the point group, yeah, there's nothing you can decorate on the 1D block, pretty trivial. And on the 0D block, we only have this Z2 square bosonic kind of root phase. So in total, we have Z26. Yeah, so now we remember these 2 results, and we try to see whether we can really match in this internal symmetry calculation. Okay. So the internal symmetry calculation is much more involved. So before going to that part, I'm just show you this classification. If we repeat this kind of slightly tedious calculation, but in principle it's simple. Yeah, you can reproduce all the classification table for spinless and spin 1/2 case. So by this real space construction. So that's a result. But we also want to examine whether this so-called crystalline equivalence principle holds or not. But here, before going that part, I just review some simple principle how to classify this Fermion SPT for internal symmetry. For internal symmetry. Yeah, for 1D, we can just view this Fermion parity as additional symmetry. It's very simple. But for 2D and 3D, yeah, there's also some more like a physical way to visualize this. But I also want to emphasize that all these kind of physical construction are perfectly consistent with the so-called spin cobordism framework first proposed by Dan and also later computed by John Morgan and his collaborators. Yeah, so our classification results for the internal symmetry group, perfectly agree with each other. Okay. Then we can just use this result to do some calculation. Yeah, so now let me show you this 2 + 1D case. Yeah, it's kind of very messy, very complicated. But the notation here, for example, 3 + 1D even complicated. So that's the whole data we need for this RTFS group spectrum sequence. We basically N1 and new 3 just a cochains. Yeah. So N1 is just a Z2 cochain. Yes, N2 Z2 cochain, and then new 3 is a U1 cochain. And then they satisfy this symmetry condition and also satisfy this kind of generalized cocycle condition. Yeah, but this obstruction function in general is very ugly, very hard to compute. But we can put all these things in the computer, and there's also a very essential way we can able to do this calculation, especially for a space group with translational symmetry Z, which is kind of an infinite group, right? But if you find a proper resolution, you can still reduce to some one-dimensional resolution. So that's the powerful part by the gap. Yeah, we just use the gap software, find the best resolution, and we can actually perform the spectrum sequence calculation based on these data. So the gamma 2, gamma 3 is something, also analog to the trivialization group. Yeah, for the internal symmetry, we can also trivialize certain data computed from these 3 cochains. Okay. Okay, so that's the result. I just show you the computation from the spectrum sequence. Yeah. So if we just look at this P4M, so we use the slightly different notation. Yeah, sometimes people also call it P4M. Yeah, P4M, you can see if we for internal symmetry, we do the we do this spinning Fermion calculation, get a Z26. So that exactly the same result as we did for the spin 1/2 system. Yeah, for crystalline symmetry. But if we put some non-trivial omega 2 in the previous formula, in this first table, we just set this omega 2 to be 0. Yeah, so that just means spinless fermion. And omega 2 non-trivial is a spin 1/2 fermion. Then we get this Z2 P4N, Z27. We exactly have 4 fermionic root phase, 3 bosonic root phase. Yeah, so you can see this data, they can be mapped to each other like, even layer by layer. All the fermionic root state map to fermionic root state and the bosonic map to bosonic root state. Yeah, so we also examined this kind of twist is very important. Yeah, spinless fermion map to spin 1/2 and spin 1/2 map to spinless. Yeah. So this is what we call the fermionic crystalline equivalence principle. But now we can also generate this into 3D. But 3D, of course, it's slightly even more complicated. Yeah. But yeah, before showing the 3D result, I can also briefly talk about this topological insulator. Yeah. So this calculation also very similar. You just put some additional U1 internal symmetry and do the decoration again. Yeah, you get a very similar result. But there's again, there's no 1D block. The result is pretty simple. Just all this 1D representation on the 0D block. Yeah, you can just figure out what is the bosonic group phase, what's the fermionic group phase. Yeah, you can again also compare with this spectrum sequence calculation. Yeah, we can also do this calculation with some additional U1, and they are all match. Okay. So now, yeah.
What's the best thing so far?
Yeah, in 2D, yeah, this map is just very simple. Yeah.
For example,
Iteration? Yeah, iteration, I think just if you think about this in space-time, yeah, if it's a TKFT, yeah, then this time direction, this first argument, this reflection symmetry can of course map to time reversal symmetry, right? If you think about the reflection, like yeah, it's a inverse. The time reversal is just a reflection in the time direction. Yeah, then this twist, yeah, because it's a fermion. Yeah, when you're doing such kind of map, you also rotate the fermion, so you get this kind of twist. Yeah, if you doing this, you want to map, for example, this mirror symmetry to time reversal, you should, yeah, twist the fermion. When doing this weak rotation, you also rotate the fermion. So you get this additional twist. Yeah, but of course, a better proof is based on the spectrum sequence. But yeah, but this spectrum sequence calculation, yeah, mathematically you can view this kind of result for the block state construction and internal space, internal SPT construction. Kind of, we choose two different types of resolutions. Yeah, but the spectrum sequence calculation proof, yeah, in this case, is still not very easy because there's differential. We don't know how to match those differentials. Yeah, so that's something we are still doing. Yeah, we try to make this more rigorous. But if you do the actual calculation and do the actual real space construction, they just match perfectly.
For example, internal
yeah,
in the system at rotational symmetry.
Right.
And as you said, reflection maps.
Right.
So what's the general underlying principle? State effect.
Yeah, just this sentence. Yeah, for this unitary, like a CN rotation, just map to the internal ZN symmetry group.
What the Professor Denry has said.
Maybe after that.
Yeah, okay. Yeah, of course. Yeah, here I'm just talking about 2+1D case. Yeah, in 3+1D, you even have something more settled. So in 3D, I think we can also do a similar kind of decoration construction. But things yeah, become slightly more complicated because now we have this 2D block, right? We have of course we have a 3D block, but a 3D block basically there's no interest in immutable state, so we don't worry about it. We just put some immutable state, yeah, some additional immutable state on the 2D block. Okay. On the 2D block, here if we really look at this like point group symmetry. Yeah, then on this 2D block, it's very similar to the 1D block we discussed previously in the 2D case. It's also some like a mirror reflection, so it also acts as a Z2 onside symmetry. So in this case, it's very fortunate the field theory for this SPT is well understood. Just yeah, just this K matrix largely not in the good theory. And yeah, when this edge state they meet on the edge, yeah, there's also this very systematic way by using this non-vector criteria to understand whether they can be gap out or not. Yeah, so just a slightly complicated, but the construction very similar. Just also show you one more example. Yeah, as a physicist, we always try to work out some example to have a better understanding. Yeah, before do the general calculation. So this we call a TD point group. Yeah. So this TD point group, the basic symmetry elements just like yeah, it's kind of C3 rotation along this diagonal axis. And also this C2 rotation along this like horizontal, vertical axis, right? So that's the basic symmetry operation. And there's also like a mirror plane. Yeah, this is like 6. Yeah, this red 6. Yeah, they are just a kind of mirror plane for the symmetry group. We can also do similar like a cell decomposition. So because this kind of group, the group elements is 24. So you can also not expect that we can like divide this whole cube into 24 small pieces. So that's a basic unit cell, like this pyramid, you can decompose into 4 pieces. Now we can again talk about the symmetry for the 2D block, 1D block, 0D block, and so on and so forth. But this 1D block, there are some slightly different class. This vertical 1D block, the symmetry is just D2 times D2F symmetry. Yeah, here again we consider spinous fermion, just a tensor product. But this is kind of D3 because we have C3 rotation and together with this mirror reflection. And then this 0D block have the full S4 symmetry. So now we can do still do this kind of block state decoration. But of course it's slightly complicated. But this result is following. Yeah, in principle on this 2D block, we can also decorate this P plus IP state, which has a Z classification. But it turns out it's not for this case. Yeah, for some other cases, we can indeed decorate this Z. And it's also very important to construct this this crystalline TI. We sometimes also decorate this kind of integer quantum Hall state. But here in our this simple example, we don't need to worry about it. It's just obstructed. Yeah, you can just check this calculation easily. And this even double layer of P plus IP is also trivial. Then another thing we know that on the 2D plane, if we have a Z2 times Z2F symmetry, that's the Fermionic Zhengcheng Gu state. So that have a Z8 classification. But for this Z8 classification, if we just put a monolayer, the root face is also again obstructed by using this Lagrange liquid K matrix calculation. Even double layer is obstructed, and only this so-called bosonic Zhengcheng Gu state, just you have in the 4 layer, that's obstruction free. So that's the only thing you can decorate. And here it's the W matrix. Yeah, so W matrix just tell you how this different mode exchange on the symmetry action. Yeah, so this WR is like a rotation, WM is like a mirror reflection. So if you look at this figure, under this mirror reflection, like 1 and 3 as exchange, right? And on the rotation, just again, this is cyclical operation. That's how we design this W matrix. And also you can find this non-vector, 4 independent non-vector satisfy this criteria. Yeah. So we can find this kind of 4 independent backscattering term to make sure such kind of decoration, 2D decoration is allowed. And if we go to this 1D decoration, again, it's very similar. Similar to the like default case, so we can easily argue that if we decorate the 4, Lagrange chain is not allowed, because this kind of there's no way to consider any kind of symmetric terms. But if we have 8, we can just easily consider certain mark term is symmetric. So if we decorate all these kind of pink and the dashed line, this 8 kind of this we call the we call it a type 2 1D block state. Yeah, so green is a different type. Okay. We call it green type 2. This is type 1. Yeah, the type 1 1D block state, we should decorate all of them with Lagrange chain is allowed. So just half of them is not allowed. Then we repeat the story. We can decorate this Z2 times Z2F Fermionic SPT phase. Yes, double Lagrange chain. But that's allowed. Yeah, even just for half of them, just for either for the pink or for the dashed line. For the pink, it's already symmetric on this full TD symmetry. And the dashed line also, this is for 1D block also symmetric under this TD symmetry. Okay. So now we have kind of 2 different phases. And also on this pink, on this green line, this vertical horizontal. Yeah, so there we also allowed to decorate this Howland chain. So that's also also allowed by symmetry. So now we can see that we have a kind of two different types of root phase. But again, we need to think about some trivialization. Yeah, so very similar to this 2D case. Once we have this 1D block, we can think about using this bubble equivalence principle to do some kind of trivialization. Yeah, you can now think about that we have this bubble on the sigma 3. Just means we're starting from nothing, then we create this Marion chain all the way push them to the boundary. After this, you can see that because this sigma 3, if you look at this cell decomposition, that's this just this outside phase. Sorry. Yeah, this sigma 3 phase. Yeah, so there are three kind of sigma 3 phase joined together along this pink line. So we end up with one single Marion chain left. Yeah, so now the conclusion is that it's kind of just trivialize our first construction. If we decorate the Marion chain on both pink and dash line, it's trivial. So that's the conclusion. And for the second case, it's also tells us if we decorate this double Marion chain, the 1D from SPT on both pink and dash line, also trivial. So finally, just tell us that if we decorate on this type 1 block, this block, the vertical one. Then we also see some equivalence condition. This kind of basically we'll just make this AQT declaration on the green chain equivalent to this 1D from SPT declaration on the pink line. Yeah. So you can see such kind of equivalent relation by this kind of bubble construction. So in the end, we only have one Z2 left. Yeah, either you can vector the AQT chain on the green 1D block, or just vector this double Marion chain on the pink. So they are completely equivalent. And all the other declaration pattern just trivial. So we only have one Z2 left. So finally, we can also think about this 0D block state. Yeah, 0D block state, again, we can have something, because it's a tensor product, right? So this is a Fermion parity, contributed by a Fermion parity. And also this kind of H of 1D representation of this 4, just Z2. Yeah, this basically, again, just a mirror eigenvalue. But a mirror eigenvalue, you can see, can also be trivialized. So in the end, the classification result is just the Z2Q. Yeah. So here to summarize about this 3 block state. The 2D block just this bosonic level. Here's the bosonic level. And the 1D block just either Howland chain on the green 1D block or this 1D from SPT on the pink. And finally, it's just a complex fermion calculation on the ZD 0-dimensional block. Yeah, but I think in this example, I think there's also calculation by Aron, I think, Dan's student before. His result is slightly different, probably. As a Z4, probably it's Z4 times Z4 times Z2 squared. But yeah, we kind of check the calculation. Maybe here there's some slightly different definition of the omega-2. Yeah, so if we use the physical omega-2, we again get this Z2Q results.
Sorry, what's this?
It's just like spinless fermion with this TD group symmetry.
You're saying Arun's calculation and yours don't agree.
Yeah, he has like a Z4 times Z2 squared, so we just a Z2Q. But we also check his calculation. Yeah, I think yeah, there's some problem for the omega-2 he used in his calculation. This kind of non-trivial extension. If we map to this, if we map to the internal, you should map to some spin 1/2 system. There's not some non-trivial omega-2. So if we correct those definitions, then everything just agree perfect. Yeah, we just redo the calculation with the help of Wei Chen. I think Wei Chen is also his collaborator. So we just checked probably only 3 cases, I think, disagree. But yeah, after we use a slightly different omega-2 definition consistent with the physical case. They all agree. So I think here we also did this calculation by mapping them exactly into internal group. Yeah, into internal group, we can also work out this spectrum sequence by using the gap software. So we just view this kind of spinning system as a spin one-half system with internal symmetry, vice versa. But there's something a little bit tricky, yeah. So like for some case, like S2 is like something like we call the inversion, yeah. So on the inversion symmetry, because it's like a combination of mirror and and this combination of mirror and rotation. So in that case, regardless it's spinless or spin one half, it's a square always equal to +1. Yeah, so when we map into internal symmetry, it's also equal to +1. So that means in 3D, this formula for this correspondence should be also slightly extended, also include the inversion, because the inversion is a new symmetry operation emerging in 3D. Yeah, but for this mirror and for this kind of CN rotation, the mapping is exactly the same as 2D case. Here we also examined in Aron's paper, but he probably computed just a few classes, and not all of them. But for those computed class, if we look physically, the physical omega-2, I think everything is agree. Okay, so finally, just 5 minutes. Let me briefly mention this how to compute topological insulators. Yeah, it's very similar to the 2D case. Yeah, we can just in the block state, in the block state, we can add this additional U1 phase. Now we get a more block state, like in the 2D block. You know, if we only have this like a Z2 reflection, only have internal Z2 symmetry, just a Z2 from SPT. But now we can have this additional U1, so we have much more things we can play with. Yeah, like for this U1 only, we already can decorate like integer quantum state. And without any symmetry, we can also put a K E8 state. And with this both U1 and Z2, we can still have this Z2 fermionic SPT phase. But now the Z8 just reduced to the Z4 because with additional U1 symmetry, this only double layer of this fermionic Zhengcheng Gu state comparable with the U1 symmetry. Yeah, so that's some additional complication for the 2D block. Okay. But we also gain some additional simplification, because with the additional U1 symmetry, we have only non-trivial root state, the Holland chain for this 1D block, for spinless fermion. And there's no non-trivial 1D block again for spin one half state, so it's pretty simple for 1D case. Also simplify the calculation. And for the 0D block, also something simple. 0D block only have a Z2, but also of course, now we have a Z. This just means the fermion charge we not have Z. But there's some like obstruction. If there's non-trivial extension, we should worry about this obstruction. So in conclusion, for this kind of so-called atomic insulators, just means for this 0D block decoration. So we just get like Z2 for spin fermion, and U1F charge, n equal to 2 mod 4 for spin is 1/2 fermion. So all of them just Z2. Okay, so that's additional complication for system with additional U1 symmetry. But we can also work out a table. So I don't show you this. In this example for TD, for TD there's a Z2 CUHK 2D block state. But I think it's already late. So and for a spin one half system, we get this Z8 times Z2 squared. With the following kind of all the root phase. Okay. So here we get some Z2, here Z2, and here we get Z8. But here we get 4Z2. So that's it. But all this calculation just a little bit tedious, but it's straightforward. So we can also work out a table. So we look at this table for both the spin one half and the spinless system. Here is the spinless and spin one half system. For the few cases computed by Aron, we also agree. So, but we here just list all the complete lists. But from the technical side, we already see that yeah, previously you can see for this superconductor, yeah, we just without U1 symmetry. Then you can see this for spin 1/2 system. Yeah, all this 2D and 1D block decoration pretty trivial. Yeah, almost trivial except this S4 case. Yeah. So yeah, typically just means experimentally there's a very hard to find something really interesting for interacting system. But for spinless fermion, there's a lot of interesting, I think, fermion SPT phase. But yeah, if we compare make a comparison with the insulating phase, yeah, for insulating, I think in general for both spinless and the spin 1/2 case, a lot of interesting interacting phases. Yeah, so that's our conclusion. So probably experimental people can also work more on this insulating phase instead of superconductor.
So the spin, fermion, the spin versus spinless, there's always a comparative symmetry.
Yeah.
What's the symmetry strategy?
Yeah, just means there's a kind of trivial extension, non-trivial extension over Z to F. Yeah. Like you have time reversal square equal -1 +1, so that means spin 1/2 or spinless. Yeah, that's just like a physical way to describe this symmetry. Maybe not rigorous in a mathematical sense, but just to tell experimental people they should focus on what kind of system.
So it was kind T squared equal -1 Fs. Spin for fermion.
Yeah, we call spin 1/2 fermion. Yeah. Or spin for fermion, usually we just refer to the spin 1/2 fermion. So this T squared -1, mirror squared -1, rotation to the certain power to -1, so on and so forth. Even the +1, we just means spinless. Yeah.
So when you map the system to other systems,
Right.
what representations you choose? Any one of the works? Any phase? How does it act? You need to choose a set of matrix that implements this group symmetry.
You mean in the internal symmetry case? Yeah, in the internal symmetry case, just like let me again go back to the 2+1D example. Yeah, so here in this table, we just fully specify this internal symmetry. Yeah, so we have the data like omega-2. Omega-2 just means whether you choose a trivial or non-trivial extension. But this omega-2 is also not unique. For arbitrary G, B, Z2, you have several different choices. You should choose this proper one. Yeah, we call the physical one, corresponding to like a mirror reflection of -1, rotation to the nth power of -1. So there's a unique one you can choose. And also this S1 should be careful. Yeah, sometimes if we think about there's a mirror reflection and map time reversal, this S1 should be non-trivial. Yeah. So we have this S1 from H1 GPP. So we specify the whole action of the symmetry actually in this page. Yeah, the omega-2 and S1 is determined by the symmetry. Yeah, once you input this, you can do the calculation. Okay, I think it's already late. Yeah, so I just briefly summarize. Yeah, before summarize, I just also briefly mentioned maybe physicists interested. They call it high order power superconductor or power insulator. Yeah, now from this block state decoration, this becomes apparent. Yeah, so suppose you have this like 2D block decoration, you end up with like this hinge state, right? So that's one of the interesting high order state. If you have this 1D block decoration, end up with a corner, corner state. So that's further high order states. So the conclusion is that in the real space construction, these high order states can be visualized in a very simple way. But in this case space for fermion, I think the high order states is really complicated. Sometimes you need to design certain like Wilson line in the brane zone to do the calculation. It's pretty complicated. So finally, just it's a conclusion. I think in general, like 2D, the most interesting case is just the P4M symmetry group. Yeah, so in the experimental lab, there are certain like a material like nictide-based superconductivity. Yeah, people try to looking for such kind of non-trivial SPT phase. Yeah, with kind of a pair of Majorana mode on the corner. So that's probably some interesting high order states. Yeah, so in 3D, probably the more interesting thing is the crystalline topological insulate. And here, I think some very important principle or some lesson we learned is that, yeah, if we think about really some topological phase, looks like this internal symmetry and yes, space-time lattice symmetry. Yeah, there's not so much difference, especially we talk about the anomaly. So we also have some better understanding if we really think about the additional bulk. So with the same bulk, we can realize this anomalous crystalline SPT phase or anomalous internal symmetry SPT phase on the surface. Yeah, just a kind of different surface. But this kind of equivalence principle we conjecture may be also useful in the future understanding for example quantum gravity. Yeah, so people believe it should be something like a gauge theory of space-time. So if we're really starting from some topological theory at the UV scale, then we conjecture such kind of equivalence principle may also hold. Okay, thanks.
Thank you for the lovely talk. Do you have any questions in the room?
Yeah.
So you mentioned space-time symmetry.
Yeah.
There's a PRL paper by.
Oh.
This. Have you tried using his groups? Try them
or? Which group?
He has some space-time group lattice group.
Oh.
I don't know if you're not familiar. So.
Yeah, maybe you can send me paper. I can take a look what kind of particular lattice group. Yeah.
Yeah, I'll just say a word about Mike Hopkins and I did. So it's really based on what Alexei Kitaev, his intuition, his conjecture, if you like, is that these phases form a homology theory. So if you have any space, not space-time, but space, on which you want to know what the different phases are, for example, phases to push forward map, but not by an arbitrary map. So these phases could exist, for example, in Euclidean space on the whole space. Homology classes have compact support.
I see.
The finite sums of chains which have compact. So it's what's called Borel-Moore homology, which goes stool to compact supported cohomology. And so those can push forward on proper maps. So when you talk about a certain phase being, for example, supported on a line inside three-dimensional space, that's the idea. So then the question is, well, and then if you have a symmetry group, a space with a group acting, you have equivariant homology. Again, you have to decide what kind of equivariant. Borel, standard Borel. So then the question becomes, what homology theory is it? And that's something that, using field theory ideas, you can identify what field theory that is.
I see.
What we did in our first paper, and so you know what field theory is, and then you can write it down. So then you have a general formula to compute all of these cases. Okay, what goes into it is what kind of symmetry type, if you like, your theory is, which means it's a fermionic, it's a superconductor. So those all are encoded by different groups, and the formula takes into account those groups. So, for example, this crystalline equivalence principle follows in a few lines. Actually, once you have the general formula, it's just a few lines in spectral sequence, right? But in general, I think there's a twisting that comes in certain cases in order to thesis. It's about.
I see. So in your paper, use this Adams spectrum sequence.
Well, that's a computational.
I see. In principle, you can also use Atiyah-Hurst group. I see.
Well, I mean, you have a homology or an equivariant homology to compute. So the conceptual thing is that's the answer.
Oh, I see.
And algebraic topology offers you all sorts of techniques to compute.
I see.
How you break up your space.
Oh, I see. I see. So probably we only repeated the calculation in Aron's paper. So he used the Adams spectrum. Slightly different from our Atiyah-Hurst group. But it's kind of very surprising that they agree in that.
Well, once you have an actual group you're calculating, stated as a homology group, then it's less. I mean, at the beginning of homology theory, it was surprising that for example, definitions of homology theory gave you the same answer. So it took some work to see why. We like that in quantum field theory, for example, the different approaches to quantum field theory do the same thing. We'd like to know what's the variant definition. But here, if you have a homology group, yeah, there are lots of different spectral sequences, different log exact sequences, different cell decompositions, whatever. Techniques you can use to calculate it. But they all give the same answer because you can express it as this homology.
I see.
Excuse me, follow this quick comments. So here, like, three objects. System.
There's one called Phases spatial symmetry, isn't it? Yeah.
But what's the way you build a crystalline equivalent? What do you understand? What's the statement?
I think the statement is that you're trying to compute these phases on a Euclidean space where you have a group acting, but the group has a fixed point. You need a fixed point. So that means the group is acting by a homomorphism to the orthogonal. And then, well, you write down this variant homology group, but for an exotic homology theory, it's not standard homology. And then you calculate it on the Euclidean space, and you do a few simple maneuvers, and you see the group you get is the same as the group of topological phases and vertical phases with a symmetry group that combines this group that's acting in the Euclidean space and whatever symmetry type you have. But that's a simple general calculation from the definition. Homology group.
So does the definition?
It's in the paper.
Does this calculation offers a explicit map between these two? Or is more like they are?
Well, there's an explicit isomorphism.
But
yes, so there's an explicit isomorphism. So perhaps you can take a description of a system. You can think of that as like a cocycle homology class. Follow that cocycle through some kind of cocycle description, spin system, whatever. But in essence, it's that. And then you would try to follow it through.
would everything translate, like transfer around to hyperbolic spaces? Their translations there, like
well, the formula in general is for a space with a, I suppose it's for set.
so it doesn't have to be there.
No. Okay, I mean, for example, on a compact
The ones that are confused about the crystalline looking at there is some statement made such that, for example, like hyperversal in that case is anti-unitary. And it maps to reflection. Is that still anti-unitary? Or unitary? In the convex system will reflect this.
Yeah.
So sometimes or the other case, let's say internal symmetry.
Right.
Unitary. It maps to which is a unitary.
Yeah, as I mentioned, in field theory, if you assume this like Lorentz invariance, you can always map this time reversal, which it's kind of T2 minus T, some kind of operation, right? It's kind of because time reversal has two different definitions. One in the field theory, you map T2 minus T, but that's kind of it's unitary symmetry. It's not anti-unitary. It's just in field theory map T2 minus. It's very similar to this mirror reflection X2 minus X. Yeah. But in Kant's matter, of course, we know if we can just acting this time reversal as an internal symmetry, become anti-unitary. Yeah. So for time reversal, we have two interpretations. So if you use the other interpretation after weak rotation, exactly the same as mirror reflection. So that's why I think there are twists from unitary to anti-unitary.
relativistic quantum field theory. Have a time reversing transformation, it doesn't adapt.
Yeah, in the field theory level, I think just you can map T to minus T. On the,
Well, if I think of. If I have a relativistic quantum mechanical system, it means I have a representation of some form of the Poincare group.
right.
And I'm saying in a relativistic quantum field theory, there's a theorem, CPT, that says that usually you have a representation of the group where you don't have time reversal symmetries. You have a time orientation. You have to preserve that.
Right.
But the representation extends to bigger group, which includes time reversal. But those new group elements act anti-linear. That's the theory. So I haven't seen the difference you're making. And it's true if you just have space, then time reversal is internal. It's not moving amounts of space. And you're saying that acts anti-linear. That seems to me to agree with what happens in quantum fields.
Yeah, I don't fully agree that time reversal is internal, because well, more like I don't think it's local in the sense that you cannot act on the system on a part of the system. Time reversal. Like there's this trick of calculating when the invariance, you could take half of the system, just act the symmetry on.
Yeah. Time reversal like UK. If you view as an internal symmetry, U part is local and K.
Yeah,
This complex conjugate is non-local.
You need to choose some
Yeah.
conjugation, and that conjugation is supported everywhere.
Yeah, that's acting in a Hilbert space. I think you choose it as UK.
But yeah. So I sort of philosophically think this K is not an internal.
Yeah, K is not internal in some sense, but I think in condensed matter sometimes we just maybe slightly release the definition of internal. We have two definitions. One is you can define as UK. The other is just a map from T to minus T. So yeah, we naturally have two different definitions, but they are equivalent, I think. Because in the Schrödinger equation, you can change T to minus T. It's allowed at time reversal. You use a complex conjugate, you also change I to minus I. So that's a trick how you can make time reversal.
Any more questions? No, let's thank Zhengcheng again.
Okay, thank you.